Good afternoon. Welcome to this first of a two-part seminar. Each of them is designed can be listened to and used as a standalone, but of course the full benefit will only come from listening to both of them.
Is it working? Yeah,
yep.
Okay.
So what do I wish to cover today? By means of introduction, I want to give you an overview on the prevalence of poor reproducibility. The core of the presentation will be to provide an overview of main causes of poor reproducibility with a focus on study design and study conduct. The presentation tomorrow will focus on data analysis and reporting. And at the end today, I will have a short discussion of the implication of more robust science. So let me start off with some definitions. I would like to define reproducibility as repeating the same study under exactly the same conditions and with the same sample size will yield a comparable answer. Not necessarily exactly the same numbers, but pretty close. In contrast, robustness means that a similar study will yield a comparable answer even if some aspects of study design and conduct are different. For example, using a different mouse strain or a different antibody. An extension of this is that a trial in humans will yield a similar answer as in an animal model, and that can be called translational robustness. And for most of the animal work we're doing, certainly for me as a pharmacologist, being able to extrapolate from my preclinical findings to potential clinical trials is of utmost importance. It flows that a study cannot be robust if it is not reproducible. So when we read papers in the scientific literature, we have the basic trust that the work we read there represents truly the real biological situation. However, this trust was shattered in 2011 when investigators from Bayer reported in Nature Reviews Drug Discovery that a major fraction of the studies they looked at in the areas of oncology, women's health, and cardiovascular medicine could not be reproduced for their main findings, and for some others, at least certain parts of the study could not be reproduced. That sent a real shock through the community, and meanwhile, similar attempts have been made by others. For example, the folks at Amgen, who focused on oncology studies, and several academic groups. You can see all of them found that at least 50% of the studies they looked at could not be reproduced. So let's do a little play of numbers here. It takes about 10 years to develop a drug, and even of those candidates who make it into the first human studies, only 1 in 8 survives and makes it to an approved medicine. And this effort in the US alone, based on numbers from 2013, which by today's standards certainly are very conservative estimates, took more than $50 billion every year. So if based on the previous slide, more than 50% of the studies preclinically are not reproducible, this means that we are wasting about 25 billion US dollars in the US alone every single year. And that's a number you really have to let sink in for a moment. Most likely, all of us combined in our entire lifetimes will not make that much money. So this is a major economic loss to society. But it actually is not only an economic loss, it also has a lot of indirect costs. For example, wasted time and effort, wasted research animals, I am a strong believer that the use of animals in experimental biomedicine is, for many things, required, but I'm also a strong believer that this, on our side, requires that we really use them carefully. And if half of the animals are used not generating reproducible data, the whole enterprise becomes questionable. There have been cases of challenged validity of patents. Drugs have been advanced to clinical trials that were bound to fail, and I'll show you an example in just a second. Approved drugs had to be withdrawn, and there are several cases of inappropriate off-label use of approved drugs based on misleading and non-reproducible preclinical data. Let me show you two examples. NXY059 is a drug that was under investigation to limit the damage by stroke. Even if you're not working in this specific area, you probably are aware that a stroke is, in most cases, a very devastating event, and most patients, if they survive, remain impaired for the rest of their lives. Malcolm McLeod from Edinburgh in Scotland is a neurologist who has been interested in stroke for a long time. And based on 9 preclinical studies showing efficacy of this NXY compound in stroke models, this drug was advanced to phase 2 clinical trials where it failed miserably. Not even a hint of a possible beneficial effect in patients. So Malcolm went back and looked at the underlying preclinical studies. And what you see here on the figure is a horizontal gray bar, and that indicates the effect size that you probably need in a preclinical study in order to have a meaningful effect in patients. And then he compared, for example, in the upper left panel, randomized and non-randomized studies. The drug in the animals worked great in the non-randomized, but not in the randomized study. In the upper right panel, you can see it worked great when non-blinded, but it did not work when blinded. And stroke is mostly something not occurring in otherwise healthy people, but in most cases on the background of an existing chronically elevated blood pressure, hypertension. Well, in animals, the drug worked very well in normotensive animals, but it did not work in animals with concomitant hypertension. So, with hindsight, this drug should have never proceeded to clinical studies in people. Let me give you another example. You probably became familiar with a disease called amyotrophic lateral sclerosis, or called ALS for short, when into the context of the Ice Bucket Challenge. There is in the US an institute called ALS Therapy Development Institute, and based on reports in the literature, they have retested more than 50 drugs previously reported to be effective in a mouse model of ALS. In this case, we can be pretty fortunate for 2 reasons. Number one, the entire community uses the very same mouse model. So there shouldn't be that much variability. It's a genetic model. Second, the endpoint is survival. Survival is not hard to miss, and you can hardly argue whether a mouse is dead or alive. And what you see here in the figure is the increase in survival originally published for a range of compounds, and all of these compounds are available for use in humans. However, when the ALS Therapy Development Institute retested those drugs in adequately powered, properly randomized and blinded studies, none of them had a measurable effect on survival. Given that ALS patients are really desperate and there is no good treatment available at all, other than some symptomatic treatments, many physicians have tried, based on the animal reports, to give some of these drugs to their patients. However, several of these drugs really are quite toxic, which may be acceptable if the drug is given for a good reason, but clearly if it's not effective at all in animal models. So what are the root causes of this poor reproducibility? Well, the good news is that outright fraud is considered a minor component only. Most people feel that it's less than 1% of cases of poor reproducibility. I have not seen any estimate ranging higher than 2%. An obvious element is poor description of methods. How often have you read a paper, wanted to redo that study or at least use that test, and then got frustrated when you looked at the methods part of the paper and had so many questions? How the heck did they really do it? This is something I will cover in part tomorrow, but not today. What I want to talk about mostly today is poor study design and poor study conduct. Data analysis and reporting are topics I will cover in the second presentation. Generally, we can take lessons from evidence-based medicine. Medicine, pressured by regulatory authorities and ethical committees, has developed high-quality standards for conducting clinical trials in people. These include pre-specified protocols for the execution and analysis, including statistical analysis, pre-specified sample sizes based on power calculations, randomization, and blinding. These principles, of course, are applicable to preclinical research as well. The main difference really is that as experimental biologists, we are handling smaller sample sizes, which imply a greater level of uncertainty in the interpretation of our findings. So this is something we have to handle, but that is not an excuse not to apply those steps to make our work more robust that can be used in preclinical work as well. So starting out at the level of study design, I first wish to talk about hypothesis testing versus exploratory studies. What do I consider a hypothesis testing, or in statistical jargon, a confirmatory study? For statisticians, confirmatory does not mean you repeat something that someone else has already done, but it means that you had a very specific, quantifiable hypothesis before the study was done, and the study was designed to exactly test this one specific hypothesis. In contrast, an exploratory study is mostly hypothesis generating. Thus, a pre-specified scientific plausible hypothesis is not required. The confirmatory study, to be taken serious as such, requires that you have pre-specified not only a null hypothesis, but also all main experimental methods, including sample sizes and analytical methods. In contrast, in an exploratory study, you can adapt methods to some extent. At the end of it, the confirmatory study leads to a statement of statistical significance, which actually is a binary decision. You reject the null hypothesis or you don't. In contrast, in an exploratory studies, p-value cannot be interpreted at face values for reasons I'll go into both today and tomorrow. Both types of studies have a place in science. They serve different roles. Some people feel that exploratory work may be of less importance. That is untrue. You could even argue the opposite. If so much evidence is already available that you can design a meaningful hypothesis testing study, basically all the really exciting, innovative ideas have already been generated. So in order to advance science, we need both exploratory work and, if that comes up with really interesting ideas, hypothesis testing work to confirm it's real. Elements of both can be combined in a single study. For example, a study may have a primary endpoint and maybe a key secondary endpoint that test specific hypotheses, whereas all other endpoints are exploratory. Let me give you an example. If you generate a knockout mouse for a certain gene, for example, one specific receptor, let's say the endothelin ETA receptor, and your hypothesis is that this receptor is important in blood pressure regulation, your primary endpoint may be blood pressure. Of course, if you go through the trouble of generating this mouse, even if it's now much easier than it was 10, 15 years ago, you will measure a lot of other things as well. Things like procreation behavior, food intake, body weight, and so on. All of these should be measured, but are exploratory additional endpoints. It's slightly different in an in vitro study, where you typically do not have one big experiment with measuring multiple parameters, but rather you have individual experiments typically only looking at one parameter. These are sequential steps, one building upon the other. In this change of sequential step, some of the experiments may be designed as confirmatory, some as exploratory. It's up to you as the investigator to see which is what as fit for purpose. One of the troubles with exploratory work is they have a lower prior probability for a certain outcome. And as I will show you in more detail tomorrow, a lower prior probability means that the chance that an observed p-value represents a true finding goes down. Actually, some people say exploratory studies do not necessarily need p-values. Funny enough, many professional statisticians now believe that p-values are vastly overused, particularly in experimental biomedicine. On the other hand, a lot of our peers within biomedicine still are p-value addicted and will consider it strange if your study does not include p-values. However, from the point of view of a professional statistician, having actual p-values may not be required at all. Reporting on effect sizes with their 95% confidence intervals may be just sufficient. So to summarize this, both hypothesis testing and hypothesis generating work is important for scientific progress. You should tell readers of your manuscript to which category the study or the specific endpoints belong. Why is that so important? Well, our brain is a poor objective evaluator of information. We receive an almost unlimited amount of sensory input every single second. The computing power to handle this enormous input would be very expensive in evolutionary terms. So our brain has developed processes to filter the input into important, unimportant, and to add value to the filtered information based on experience. And from an evolutionary point of view, actually, there are only three key questions. Can I eat it or will it eat me? Is it threatening? And is it suitable for reproduction? These skills were important for survival as a species, but they are less helpful for today's science. Our instincts can often lead us astray. We as humans tend to be overconfident, jumping to conclusions, seeing patterns in random data, underestimating variability dependence on sample size. We are fooled by multiple comparisons and we ignore alternative explanations. As an example for that, I will show you a very short video on the next slide. It's a video of a train of the London Underground in an underground station. And when that short video starts on the next slide, I want you to decide within the first seconds, is the train you are seeing entering the train station or is it leaving the train station? Decide within the first seconds when I now switch to this mini video. Okay, actually, whatever you have decided, look at the video and think again. If you thought the train is entering the station, see whether you can also see it leaving the station and vice versa. Actually, the train is not really moving at all. What you're seeing here is a flicker picture and not a movement. So in the very first impression you got your mind set for a certain interpretation. And that directed your further looking at the short video. As early as the 1960s, an investigator by the name Rosenthal made an interesting experiment. He took PhD students and as part of their training in neurosciences, let them do a maze performance test. It's basically a test looking at how smart an animal is or whether its cognitive abilities are impaired. And for this purpose, he gave each group of students a couple of rats from a strain that was bred to be very smart, and a couple of rats from a strain that was bred to be somewhat stupid. And over again, the students, as part of their training, found the bright rats performed better than the stupid rats. Well, the students did not know that they actually were the guinea pigs in this study because all rats were from the same strain. And it was just that they had been told they were looking at smart and stupid rats that suddenly they found the so-called smart rats to be smarter than the so-called dull rats, when in reality they were all the same. So all these investigators were biased, and that affected what they measured. This applies still today. Here again is data from a paper from the group of Malcolm McLeod, in this case from Emily Sinner, who is now a junior faculty member in Edinburgh. And they went to a scientific meeting and looked at all posters reporting in vivo work. They grouped the studies into having a so-called neutral outcome or a positive outcome. And they talked to all the investigators and checked whether the study had been randomized and or blinded. Having applied randomization, about tripled the chance of getting a neutral response, and so did blinding. And studies using both randomization and blinding had a 5-fold probability of finding a neutral response compared to those that applied neither randomization nor blinding. And I have shown you this slide before that big effects of this experimental drug NXY059 were only observed in the non-randomized, non-blinded studies. And this is a frequent phenomenon. Again, the group of Malcolm McLeod analyzed about 2,000 random publications with preclinical CNS findings. And they did this from the time period 92 to 98 and from 2008 to 11. The good news is randomization and blinding became more frequent over this time period. However, when you look at the scale of the x-axis, you get somewhat depressed. While there was progress, it was so slow that even in the late 2010s or late 2000s, it was not more than 1/3 of study applying one of the two. If progress continues by that pace, it will be something in the 22nd century when finally the vast majority of study applies randomization and blinding. Frankly, I plan to be retired by then, but most likely I'm dead. Let's switch to a slightly different topic, bias. Bias is a systematic error. It can occur at each level of a project, study design, execution, analysis, and reporting. And blinding and randomization are procedures to reduce our bias. Typical bias are the selection bias. That means you assign different samples to one group than another, and that's why we wish to apply randomization. Performance bias, where knowing to which group your sample belongs, unconsciously you judge it somewhat different than if you had thought it belonged to a different group. And that can be addressed by blinding. Same applies to the detection bias or to attrition bias, which I will talk about in just a minute. Our best protection against bias are pre-specification. There is a big temptation. We have done an experiment and we have obtained a certain outcome which we didn't really like. For example, because it went in the right direction, but the p-value was more than 0.05. So there is this temptation to modify design elements or analysis elements retrospectively. However, any post hoc design, specifically if this is not transparently disclosed to readers, no longer answers a question, but rather it massages the data to a desired outcome. The key protection really is pre-specification. Specifying the treatment protocol, if applicable, including positive and negative controls, sample size, the endpoints, which are primary, which are secondary, analytical methods, and statistical methods. A third major aspect of robustness and study design is statistical power. Statistical power, in statistical terms 1 minus beta, defines the probability to detect the difference at least as large as you have specified with a given sample size and data variability. So an 80% power, and that is standard for clinical studies, means beta is 20%. This cutoff of 80% is somewhat arbitrary, and it should depend on the purpose of your study. High power is driven by a large effect size, a large sample size, and low variability. The lower the power is, the more type 2 errors you may have, such as false negatives. Let me explain this concept by an analogy. A child is sent to the basement of the house to find a tool. After a while, she comes back and says, "It's not there." Well, is the tool there or not? It depends. How long did she look? That's sample size. Is the tool as large as a snow shovel or as small as a tiny screwdriver? That is effect size. And finally, is your basement a real mess, like mine, or is it well organized? variability. Unfortunately, most studies in experimental biomedicine are vastly underpowered. I already told you that in clinical medicine, we typically design a study to have at least 80% power. Dr. Button, in this paper in Nature Review Neurosciences, took a large sample of preclinical studies, and he took various meta-analysis to estimate what is true effect and what is the true variability of a finding. And with that knowledge, he performed power calculations and looked at whether the reported studies had good, low, or high power. Only 1 in 7 studies had a power of more than 80%. Remind you, that is the standard for a clinical study. Only 1 in 3 studies had a power between 30 and 80%, and 57% of studies had a power of less than 30%. No ethical committee would approve of clinical studies with such low statistical power. To give you another analogy why small sample sizes can be so misleading, I found this cartoon. As you can see by the white coats, we have a number of scientists, and they're all looking at an object. Most of them are elderly, so they're short-sighted. And depending which random sample of the object they're investigating, they come to vastly different conclusions. The gentleman at the left thinks it's a spear, one thinks it's a snake, a tree, a rope, a wall, or a fan. For those who haven't realized this yet, the true answer would be it's an elephant. Let me give you another example how small sample sizes can be misleading. And that actually is an example that is based on a statistics course that I gave in Cologne at your graduate school. So the participants of that course took a database of 1,335 real values. In this case, from a clinical study, baseline values, how often did people go to the bathroom to leak urine per day? And each picked 20 random numbers and then looked up the corresponding patient number and read the value. And then calculated a mean of this 10 values in group A and group B. And that you see on the second panel from the right, from the left, sorry. What you can see here, the group mean of n is 10 differed from as little as 10 to as much as 18. And in the second group, again, a lot of variability, and the value in the first group could be vastly different than the other. So the calculated group difference between these two random samples ranged from -4 to +5. In the specific indication for which this database had been collected, the best available drug has an effect that exceeds that of placebo by 1. And here, in random samples, we saw effects all over the place, from -4 to +5. So many of those effects would have looked as really exciting findings. Several of these random samples found difference with a p-value around 0.1, and you have a really exciting finding and a p-value of 0.1, you start to get highly interested. In one case, there was even someone who had a p-value of 0.0002. And if you get a big effect size and such a low p-value, you think you struck gold, you really found something. Well, in this case, none of them found anything because all the samples came from the same group. There was no difference. And if you think about it, most of us in experimental biomedicine rarely use an n is 10. In most cases, we use smaller sample sizes. So this already is an over-optimistic picture. Let me come to study conduct. One of the key problems here is attrition. Attrition is a gradual reduction in number. These can be dropouts, subject lost to follow-up, or incomplete outcome data, and it occurs throughout the study. One key issue is when we as investigators actively eliminate value from the data sets. And that's often called an outlier removal. And that can systematically change and distort the study results. Well, an outlier is a value so far away from the others that it appears to have come from a different population. There can be various reasons for that. An invalid data entry, such as a typo, a missing decimal, and so on, an experimental mistake, such as double pipetting, but it could also be biological diversity, it could be random chance, and it could reflect a highly skewed distribution. The latter point I'll talk about tomorrow. The problem is if you have outliers, they can spoil the analysis. They can create the impression of a difference or association if there was none. They can block the discovery of a real difference or association. In general, non-parametric tests are less sensitive to outliers than parametric tests. Remember, we as investigators are highly biased, so we really are unreliable witnesses to identify outliers. What should you do before removing outliers? Well, ask yourself, was there possibly a mistake in data entry? If so, fix it. However, to not correct one bias with another, if you change to check for mistakes in data entry, do not only check the suspicious value, check all values. Is extreme value code for a missing value? Some older software coded missing value as 0 or as like 9999 or something like that. Is there evidence of an experimental error, such as double pipetting? If you're working on a multi-well plate and see that one well has a value about twice as high as expected based on the surrounding values, and the next one has a value close to 0, chances are you double pipetted into one of the two wells. However, often it's not so easy to find experimental errors post hoc. Therefore, whenever you suspect something occurring during experiment, try to take a note and not only post hoc think about could there have been an error if you see a value that doesn't fit. Could it be representing biological variability? In that case, it may be an exciting finding. There is a story when in the 1960s, several people worked with the same cell line and all found that a certain treatment killed most of the cells, but some cells were not killed. Most investigators in this field thought, well, that's outliers. Only one of them said, well, isn't that interesting? It's so consistent. And he went on to systematically research that. And this research ultimately got him a Nobel Prize for the discovery of G proteins in adenylyl cyclase, which is the late Alfred G. Gilman. Finally, is the sample possibly from a population with a non-Gaussian distribution, and that could potentially be fixed by applying log transformation. So coming to an end, I would like to talk about the elephant in the room. Based on the slide with data from Emily Sina, I showed you that applying randomization and blinding quintupled the chance of obtaining a neutral finding. And even if you only very recently started your PhD work, you probably already heard that a neutral finding is much more difficult to get accepted in a good journal than a so-called positive finding, even if the positive finding is untrue. If we apply more rigor in the design, conduct, analysis, and reporting of our studies, we will have more study with neutral results. And at least in the short term, this may lead to possibly fewer papers. That's not exactly a very tempting proposal, particularly not for a young graduate student. And that's a phenomenon that in English is called the elephant in the room. There is a big problem, everybody knows about it, and people don't talk about it. Why should we nonetheless strive for the most robust science we can do? Well, there is this ethical imperative that we as scientists wish to discover something real. Well, great aspirations are fine. However, if you have 4 months left before you have to hand in your thesis and need that one paper accepted in order to submit your thesis, other things may be even more tempting. A more mid-range factor is if scientists cannot be trusted, public support will diminish. And mind you, most of the money that pays for our salaries as scientists and for our experiments comes from public sources, be it directly from the government as professorships, be it grants to run a certain project or pay for a stipend. And if society no longer trusts what we as scientists are doing, this support will diminish. In the United States, for example, US Congress has told the NIH very clearly, if you cannot get this problem under control, we will not continue to provide such generous funding. Finally, the most immediate consequence is if all major projects, or most major projects, consist of experiments built on one another. If you do a poorly reproducible experiment in year 1 of your project and then build on that, you will waste a lot of time because you will find out down the line that you have been chasing a phenomenon that is not reproducible to begin with. So to conclude this with a quote from William Edwards Deming, it's not necessary to change, survival is not mandatory. And with that, I conclude today's presentation